All right. So, what might the future of the moon look like? A multi-base lunar operations from system architectures overlapping the physical constraints and the thermal feasibility around how to operate on the whole of the moon. I'm an agricultural scientist by training, so plant pathology, entomology, soil and water science, everything from food safety, really from seed to produce shelf. I've worked throughout the agricultural industry, both in organic and conventional agriculture, and really an accidental founder of Grow Mars, which is how to use bio-derived plastic in kind of an expanding loop architecture, as I saw an unrealized potential there. We have a US patent issued and continuing to gain traction into that deep tech of how to really outpace entropy, if you will, maybe for this audience, and stay in a big way on Mars. And then recently, this year, came up with a concept and a business named Moondrops. And that's what I'll be sharing today. So really, this is a two-base solution for how to operate on the whole of the moon, a North Pole base and a South Pole base, and really using long-range pressurized rover activities. It's a long journey. There's a lot of challenges, but in this way, really from a life support system standpoint, a lot of unrealized potential can be gained and a lot of economic return can be gained as well, kind of drawing the system boundaries big enough and capturing the whole width of the activities there. It closes the business case of operating on the moon in a way others may not. So what might this look like? This is a pretty concept art view of what it all looks like. Maybe a space elevator tether down to 0, 0. If you look at the moon, like a target right at 0, 0 would be going from L1 down. And the feasibility of this is rather interesting. You can have a pretty significant tether potentially operate in the hundreds of kilograms payload capacity. You don't need carbon nanotubes. You can use things like ultra high density polyethylene and just a fraction of the world's manufacturing supply, looking at like 4 days of Dyneema production to do a seed ribbon that would have potentially some minimal capacity. An interesting element to this is I had years ago ran the rough numbers on what would it be like if you had that 14-day window to traverse. How big would the solar panels have to be? Is that a feasible thing? And then you can drop off your waste resources and then have time on your side at either end of the equation to do the processing and to bring those back into usable resources to resupply. So the basic concept of operation is unlocking some unrealized potential around using those extreme conditions at the polar regions and logistically capturing the whole system. So this is a couple kind of off-the-shelf technologies, supercritical water oxidation and cold trap purification. These are things that have been widely published, but they never had a near-term place in architecture. So how to put those in rather than further down the right is really architecting this from the right, is where are we going? What are we trying to do? And then work backwards from there. So what does this roadmap look like? Again, just to put it in black and white. So North Pole base, this may be an area that is uniquely capable of doing consistent power and compute processing. At the equator, again, you've got the lunar elevator, potentially up mass, down mass, that saves a lot of propellant needs going in and out of L1 versus up and down from the lunar surface. And at the equator, that's where at the equatorial regions, you have helium-3, that's a main target there, a main abundance there. Helium-3 is mostly in those equatorial regions. Platinum group metals, you have the potential of that throughout. And then the Apollo landing sites, of course, with being respectful to those sites and having kind of safety zones around those and preservation zones around those. But those are a big interest. And there are some scientific elements to revisiting those sites as well in a respectful way. And the South Pole base science, and we all hear about the lunar South Pole and all the stuff there from the science and from the resources, but particularly carbon and nitrogen in those PSRs, those permanently shadow regions, that is a unique, very limited access. There's actually half as much nitrogen as there is carbon in those PSRs. And nitrogen is a big constraint for staying in a pressurized environment, both on the ISS and in future lunar applications. And on the far side of the moon, that's unique for radio astronomy and also helium-3 potentially. And for this audience, what does that look like from a wireless standpoint versus fiber optics using just optical communications is to preserve that area of radio silence on the far side of the moon may take some considerations as well. So to go over some of the options here, JAXA is under development of a pressurized rover, the Lunar Cruiser, and the Italian Space Agency in commercial partnership is developing the multi-purpose habitation on the right there, upper right. So really the surface mobility is how could we maximize this and leverage this capability, and what is it bound by? And how simply, what's the minimal viable architecture for making this radically expandable and cover a lot of distance? So here's just some early concept art on how that might look, taking into factors, particularly on the right image of radiation, as how to maximize that radiation shielding. We have some additional concepts in there as well. So more recently, we've been de-risking this with a lot of thermal and logistical modeling. And I'm not going to go into too depth into any of these slides, but this is just the workflow that we're currently underway with right now, really holistically looking at it and defining those constraints, working with some top class space architects that have had industry experience in these types of scenarios. Really grateful for that element is grounding this and knowing the current state of the art and limitations, and then also what hasn't been considered yet. And this seems to be an option that has not been thoroughly considered. And then for route options, there's definitely a trade-off. What's emerging from the study is solar availability versus thermal moderation. If you are in that 14-day sunlight period, there's trades to make and some de-risking elements, and to maximize capabilities as well. How do we capture the most solar power in making one of these traverses? It's being developed in a way where we can do a lot of sandboxing within this environment. I think largely that's something that has been missing when considering how to operate on the whole of the moon, or even specifically in certain lunar locations. This is a quick, just generic snapshot, not with all the parameters in there, such as shadowing and solar gain, but this is approximately what the interface will look like with a few more layers added onto it as well. And much of the data is being pulled from open source data sets. It's how we're modeling within those. And for vehicle inputs, not going to get too into the weeds on this, but it's really how does that lunar environment drive the vehicle geometry, drive the power constraints, drive the whole system. We're spiral process developing that and figuring out where some of the limitations and where some of the opportunities are. A lot of the current rover designs are for polar regions, pressurized rovers in particular. So how to make one that's adaptable to both the polar regions and the equatorial regions is a key aspect, but it seems like there's some definite pathways forward there. So again, just on some of the trades, some of the early findings, just to put this out there, is where will the solar panels double as shading? Where are the higher thermal risks? How to de-risk certain situations? How do even things as simple as windows become a problem or a solution? And how to have radiators positioned in certain ways. A lot of in the weeds thermal stuff, but interesting and important work to de-risking this large system concept. This is what you'll often see as the pathway. Again, trying to think of this as architecting from the right, is you'll see numbers common like this. Okay, we need tens of metric tons per year, even 100 metric tons per year down to the lunar surface. That is a lot of delta V, right? A lot of fuel propellant requirement, and ultimately a lot of dollars at the end of the day. And I think this could be pretty massively disruptive. I think one of the questions that we should be asking is, are lunar surface stays easier from a mass and volume and power standpoint compared to low Earth orbit? This seems like a rather unbound question at the moment that we're digging into and further seeing how far we can go, really. And can we limit consumption to under 200 kilograms for a 14-day mission? This is just a snapshot. These are baseline numbers, basically from the ISS. We've been on the International Space Station for over 25 years. And this is just what humans require, is you have to remove about a kilogram of CO2, oxygen, about a kilogram, water, 2.5. The urine in particular is an interesting one because actually 90% of your nitrogenous waste streams is in the urine, which is rather easy to recover that nitrogen from rather simply. So I often get asked, where's biology going to fit in? How do we get biology to work for us? I think that is a sweet spot. And there's a lot of off-the-shelf technology to get us there rather simply. So as you have a pressurized vessel in space, you're always getting this thing called leakage. And that's just a leakage of pressurized air through airlocks and through doing EVA activities. It's better for the lunar surface versus the International Space Station, but it's also this inescapable reality. And there's not a lot of easily accessible nitrogen sources on the moon. Water is often talked about when going to the moon, but nitrogen is a real kind of first principles challenge when anywhere in space, whether it's in orbital or on the lunar surface. Mars, we don't have that challenge though. Lots of CO, lots of relatively easily accessible. The Mars atmosphere is 3% nitrogen. So really some unbound opportunities here that don't seem like they're showstoppers. We often hear about the extreme heat and the extreme cold on the moon. What we don't hear about as these being potential resources is, can we use those? Can we use those in some of those operations for doing supercritical water oxidation to recover a lot of those trace gases and the messy organics and such? And can we, in the cold regions, do that cold thermal trap air distillation, if you will, to get out the other end a really high quality nitrogen source? Those are things that have been considered. And again, you may not need to go into a crater to do cold processing, cold air revitalization processing. You could as simply as dig a trench in some of these, especially high latitude locations right near your habitat. So all the operational considerations and challenges of getting down into one of these PSRs may not be a necessary requirement, as you could just make your own artificial PSR trench right near your habitat to utilize that cold environment and have it do work for you. Here's just a quick look at the materials and the thermal role in considering. And that dovetails into that is, what does a habitat look like on the lunar surface? What does a base look like? The thermal modeling shows that it should probably look more like a garage or a carport. That image on the left by Planetary Shelters, that's a totally separate entity. But I think that's a big element here that could be utilized. One, you can essentially move your mobile base, if you will, to different areas seasonally. So as the environment becomes more or less thermally favorable, you can put it in there. The reason why you don't want to cover it, why I have the red X through there, is you really don't want a regolith igloo. Is the thermodynamics of that they require power and radiators to function in order to keep that cool. And it's something that's rather non-intuitive until you think of it this way. If you have a human basically in a vacuum insulated thermos, and you're kicking off 100 watts of heat, that's almost like a candle inside a vacuum insulated thermos, a heat source that's continuing. That, even in a lunar night environment, overheats. So you often hear on the robotic side, survive the lunar night as a big thermal challenge. Actually, when humans are in the loop, you have to worry about heat rejection in many of these habitat scenarios, even during these 14-day lunar nights. Now, of course, there's a lot of other component considerations that need either protection from the extreme cold or extreme heat. They need some thermal regulation. But actual just human survival in these systems, having that sandbox environment to workshop some of these elements, I think, is pretty key. The other one is exhaust plume. When these rockets are landing on the lunar surface, you have a lot of ejected material. That high velocity ejected material will damage things. So the inflatable kind of carport thing, that's actually filled with regolith. I missed that detail. Is the rover parked in there? That's all actually, I believe, air inflated and then filled with regolith, definitely containing regolith. So that is going to mitigate any ejected material. That's your blast berm, if you will, and shelter from ejected material from landings or crashes. And on the radiation side, it's also protecting. You need about a half meter to a meter of regolith to really reduce that deep space radiation as well. So if you overlay those constraints, if you overlap those design constraints of rocket exhaust plume, either yours or others land, even if you have a landing pad on the moon, do others have a landing pad? Do they crash, hopefully unmanned landers into the moon and have ejected material? As we put more assets orbiting the moon, are they going to deorbit? Do we have those kind of disposal sites on the moon predetermined? That's still being worked out a lot. Thermal management is, again, you don't want that regolith maybe directly on top of that habitat. That hoop-based architecture, that kind of cave-like architecture is an ideal thermal environment because you can still radiate some of that heat away. Just the lunar regolith is really highly insulating. Being able to radiate that heat away from the habitat directly can be really useful. And then deep space radiation shielding, you need that thickness as well. And then, interesting enough, from the Artemis 2 mission is they had all those flashes on the lunar surface that they had noticed. So micrometeorite or meteorite impacts could be much higher than we previously thought. So if you overlay that additional constraint as well as ejected material from those, that is another potential factor to mitigate. Into what does this mean for infrastructure on the moon and the internet? So again, we're developing this kind of universal simulation core thermal workflow framework to use across a lot of different things, from the vehicles to the habitats, the infrastructure, to really baseline a lot of the just hard realities of infrastructure on the moon. And for surface power stations, we've identified how to align the power generation array grids with infrastructure in a way that within, again, these long traverses, these 5,500 kilometer traverses from pole to pole, that's a stretch. If that can be achieved, though, there's a huge return on investment from all the samples along the way, both the data and the physical samples along the way, and any servicing that we can do to landed assets as well, either upgrades or other tasks. But on the power standpoint, on a more short-term element and on a very buzz kind of data centers on the moon type of approach, what would that look like is with really extended range operations. We've identified the potential of within a 300 kilometer operating infrastructure, 90 megawatts of power. And for data center, if these numbers are correct, don't hold me to them, 35,000 TPUs, processing units. And based on those rates, that's a considerable revenue per year. Again, there's efforts underway to make solar panels out of actually lunar regolith. So how much of this would need to be shipped versus do you send the factory to make solar panels on the moon? That's another layer to this. But even shipped assets with those types of numbers, it could be a significant future power and infrastructure approach to what we do on the future of the moon. So going back to the moon, this was just from last week. This was the last guy, the 12th person to walk on the moon, Harrison Jack Schmitt. Fortunate enough to see him in person and talk, and he gave quite the lecture of geologist. He was all data numbers, which was really awesome to geek out over and see. And yeah, it was really interesting hearing him talk about walking on the moon. He had mentioned he did a lot of Nordic skiing, and that Nordic skiing practice was very similar to how you shuffle on the lunar surface. And he reckoned he could keep up with the rover. He said, we never had any concern if the rover broke down. They had one of the longest rover surface operations. And they would go in a way that they could walk back if the rover broke down. So it was a circular path. But it was surprising to hear that. No concerns. If that rover broke down, we were going to be able to walk back just fine. And interesting enough, I ran the numbers, is if you had a scopically stabilized EVA suit, you actually might be able to run 20 to 30 miles per hour. So he reckoned 6 to 8 miles per hour he could run shuffle on the lunar surface. And actually using gyroscopic stabilization, you still have a big mass with you, right? That inertia along with a heavy suit could be challenging without a gyroscope to stabilize you. But with that, you might be able to achieve some really high speeds, much higher speeds actually than you would need the rover to operate to do one of these traverses from pole to pole. And then this was a fun one, how space is inspirational, is that's actually the NASA chief scientist, James Green, trying on a VR headset, and my son sitting there. This was at Jack's talk just before it. And Jim was trying it on before my son was, and then my son was trying it on. It was so interesting watching the two of them go back and forth. And yeah, just space lights up the imagination, both young and old, and what our future in space looks like has yet to be determined. So thank you all for attending, and glad to answer any questions.
Fantastic. Thank you so much. So I will remind everyone, we have a Q&A section just to kick us off. I have a question, which is, given all this amazing work and even the newer additions, like you were saying stuff about these micrometeorites, where that's a newer consideration, what is the best way to keep up with your work with Grow Mars and Moondrops too?
I have a hard time keeping up with it. We have some pre-seed funding to do some of the study work from a longtime friend and angel investor in this. That's great that we were getting the engineering and modeling and really that sandbox, that missing element completed in validating a lot of this, because I think it's just something to work larger. So I think that as a service through our subcontractor will be available within the year, and we'd be promoting that openly. I came out of the hackerspace, makerspace environment, so I'm out of the open source arena as much as I'm commercially pursuing these things. So yeah, I think there'll be some opportunities to engage and sandbox some of this.
Fantastic. All right.
And I should have included patent pending. We did file provisional patents, so everything included in this is covered, but I did forget to include patent pending.
We can slide that in before we distribute.
Yes, before distributing, I'll slide that in. This is actually the first public presentation of any of this. So this is outside of kind of sideline conversations. This is the first presentation of Moondrops.
Very cool. Lucky us.
Yes, broke ground here.
All right. Another question we have, why is the North Pole more suitable for high power for compute and processing?
Topography it's much flatter. So without getting into some of the specifics, IP surrounding this at the moment, it's easier to operate on. There's more options for continuous power given that topography, because otherwise you get these really long shadow regions. When you're on the South Pole, you have the topography and the low light angle. You get these points where you have a lot of sunlight, but then you also get a lot of shadowing. And then seasonally, that varies a lot too. It's a 1.5 degree axial tilt. And you actually have a summer. People don't think of summer on the lunar poles, but it's a thing. There's actually a summer and winter. It's every 240 days on the lunar surface, which is interesting. It's unpredictable in that regard, but that's an element that does significantly impact these operations.
All right. There's another question, which may be from the same person. They submitted anonymously, but also just why the focus on the poles?
I think because, one, the South Pole has a lot of interesting science there. People want to go to the South Pole. They want that PSR water. That's an unshakable narrative, as much as we have other areas to meet those demands within the system. I think it's just a good turnaround point more than anything. And I don't think it's the absolute South Pole. Just to be clear on that, I don't think we have to go all the way to the geographic North and South Pole. There's a kind of a sweet spot there to do a turnaround without getting into any specifics. So yeah, I think that's the stretch. And you do have those peaks of eternal light that are relatively accessible. Those peaks of eternal light where you have a lot of available solar power, they're on the ridges around there. So if you're going after long periods of illumination, you don't have to go all the way, but you do have to go pretty close, within a couple 100 kilometers.
We have a longer question from Scott Johnson, and I want to make sure that I get this just right. So I want to read it word for word. Developing computing environments for lunar operation is similar to doing it for remote locations on Earth. Hard power budget being a key factor. I would suggest that assuming the solutions that would work in a terrestrial data center environment will work on a hard power budget is the wrong approach. The hardware needs to be designed or chosen for its power efficiency properties. What thought has been paid to this factor when considering lunar surface data centers? Have non-AI workloads been considered, as services like web and mail are known to be desired on the lunar surface?
Yeah, not specific services, just that raw compute. And I look at it as the industrial AI. There's a long latency period there. So where can we do a lot of the heavy lifting that latency isn't a big challenge, and what's scalable? What that future looks like, I think stepping back to the whole of a moon approach, like all the way back to helium-3 and such, is helium-3 could be used for power generation on Earth. It could be used for supercomputers on Earth. We could just have to brute force it and do solar panels and data centers on the moon, right? There's solar panels out of lunar regolith. And so whatever the future looks like, there's this interesting overlap with the moon being part of our future. And don't know what it's going to be. Is it going to be supercomputers? Is it going to be helium-3 used for nuclear power generation? Is it just going to be brute force? We need surface area and we need materials to make solar panels. I don't know what that future looks like, but this has enough stakeholders and closes the case. Everyone's very heads down on different technological approaches, tech areas of what to do on the moon, on the next steps. And this just seemed like a missed opportunity. This just seemed okay. If you take the whole approach, how does this all look? And does that hardware business case close for the cost of these elements? Because it's in the billions. Do the billions add up? Can we put 5 to 10 billion in and operate in a way where we have $5 to $10 billion of return, both scientifically and economically? And so this was one that just seemed like it closed. So what's unique to the moon versus Earth for data centers is it's the coldest place. Is actually, you don't think of it, but when you're in the shadow of the Earth is still radiating heat off. So you actually don't get as cold in the Leo night as you do in the lunar night. So the lunar night, you don't have that body kicking off heat as much as you think of the dark Earth. You don't think of that as kicking off heat, but it is. The lunar environment is actually the coldest environment near Earth, like by a long shot. But you can design hardware to operate at different thermal temperatures. So where it can be, I think it gets down to more the infrastructure is where we're identifying some capabilities is how do you co-locate infrastructure along with power generation along those thermal constraints? That's actually what's looking like the benefit of doing it all within a certain concept of operations. I can't go into too many details there, unfortunately, but yeah, I think that is the big difference is that thermal environment and that infrastructure is just that infrastructure. You have to mitigate that to a certain standpoint and how do you utilize that again as a resource, but then also mitigate that factor is an important one that is just unique to the lunar surface.
So in that answer, you addressed the comparison to Leo and the economics. And we do have a question from Scott Burley, which was saying, are the lunar data centers, as proposed, economically competitive with proposed Leo data centers? And if not, what would need to be developed to bring them to parity or superiority?
Yeah, for those who may not be familiar, Blue Origin has a Blue Alchemist program where they made solar panels out of lunar regolith. So that was a tipping point grant done a few years ago. So can you make solar panels out of lunar regolith? That's been answered to a certain extent. So what does that look like? Bringing the factory that makes solar panels on the moon and then kicking those out, that's a rather unique thing. I think we'd have to send the TPUs, however they look, right? Whatever the compute looks like. So yeah, the orbital station keeping, it's a requirement both for lunar and for Earth. So that takes a lot of energy. If we have an abundance of really cheap energy on Earth, maybe propellant isn't an energetic factor and limiting factor. But that's just a hard aspect of it. Now, the economic return is way higher for Leo, I think, is you've got Golden Dome, you have all these other driving factors in the hundreds of billions of dollars for non-terrestrial networks that play into all that. So on the other side of it, how do you balance those? Is right now there is really no demand signal for a lot of compute on the lunar surface. It's in Leo. But long term, if you draw it out 50 years, 100 years, not even that, right? If you draw it out 10, 20 years, what does that look like? It could look radically different. It could look much more organic and brute forced versus launch constraint, if you will.
Very cool. We do have some questions coming in, of course, about the networking to enable this project. We have a question from an anonymous asker asking, what are the communication networking requirements for this?
That's a great question that is above my life sciences experience. Earth line of sight, maybe I didn't mention that, is just having these base of operations and having those infrastructure elements be line of sight, both to L1 and from the lunar surface back to Earth, or some other point to be determined. I'm not sure. Maybe it's L2, L4. Not sure what the future of the cislunar space is going to look like. So I think just being cognizant of that and the expansion of optical communications as well. But then the economic reality of we spend a lot of money to go into deep space. Those Artemis missions, it was $10 billion a day for Humans in the Loop. And it was $100 billion plus program for 10 days. So how to really be cognizant of what's the return, how to really do this organically and thinking beyond the rockets basically, and how to accomplish these things, I think is a opportunity. And then humans in the loop, I'd suggest, is also a critical factor. If you have these billions of dollars of assets on the lunar surface, the risk profile changes when you have humans in the loop, because you have often the debate robots versus humans. Why have humans as part of it? And I think that really changes the risk posture. Is once you have human assets there living and breathing and working on the moon and they can pay for themselves, it might be pretty expensive to have humans on the moon. But if they're returning the value of being there, either directly or indirectly by being present, it may look a lot different. You could think of that with like satellite testing and ASAT testing is destructive satellite testing. If we didn't have people living in LEO, what would ASAT testing look like? That is probably very different with the ISS and with other space stations.
Interesting. With that theme of human in the loop versus humanless environments, there is a question asking, will internet towers be mobile, similar to the lunar base or shelter? And will the rovers and other devices be autonomous? Yeah, if that is known and disclosable.
So the internet towers. So on the far side of the moon, that's an interesting one with that radio silent region, right? Is probably no wireless communications there. Of course, wireless is weird when you think of fiber optic, right? Wireless, right? But yeah, on the far side of the moon, it's interesting. And then what that means for other assets is how do we really preserve that radio silent? Because that's the place to put those radio astronomy, that radio silent region. If you want to build really big observational capabilities on the far side of the moon, I think that's a great place to do it and should be preserved. That's my only insight into that. That's the only constraint I'd put around that. Otherwise, unknown.
Fair enough. I have a question from Lee. Said, there is a considerable difference in the power and cooling requirements between data centers and AI centers. Were the power and cooling requirements for AI centers looked at, or are you just targeting data centers right now?
I only tensor processing units. That's the only number that I looked at very topically. So interested in exploring those differences more and what that might look like. The challenges of the lunar surface is that regolith that's highly insulating is you can't use that as a heat sink really. So you have these cold areas that you can radiate away. But again, it's really more about, I think, matching your infrastructure and degradation of your infrastructure, your thermal degradation of your infrastructure, and moderating everything. And that's where I think there's a unique potential of doing that on the moon and you can't do that in orbit. Orbit, you're constantly thermally cycling. So that really high rate of thermal cycling is what you're trying to mitigate against. And that's one of the key elements of how to operate data centers there. So different thermal loads, that's good to consider. And I'll have to look more into that.
A question from Scott Spicer, my brother. Hey, Scott. Can you explain Grow Mars, and how did you get into space and lunar exploration and habitation as a field?
Yeah, totally by accident 10 years ago. I was working a lot with plastics and agricultural systems, and I was interested in the environmental fate of them. And there was these things called bioplastics that were being thrown out there as green alternatives. But when you looked into the chemistry of them, it was surprising. It was like, hey, this is still polyethylene. What's going on here? This is the same plastic. And at the same time, 3D printing was coming about. And it was 2015, 2016, SpaceX was landing rockets. People were talking about colonizing Mars and stuff. And the future looked like, to many of these people, we're going to have nuclear reactors and robots do everything for us. And I was like, how do you make another nuclear reactor? Like, how is that expandable and such? And I just imagined, what would it be like? It's really weird. There's this curious fact of not all bio-derived plastics being biodegradable. What would it look like if you had an initial greenhouse and you processed all the inedible root stems, leaves, or whatever other biomass into another greenhouse? What would that look like? And that's actually where I ran down the thermal rabbit hole a lot. That was really interesting to model greenhouses on Mars. And that was how I identified this thermal blind spot to a lot of the space modeling, is because it's very non-intuitive. A greenhouse on Mars warms up very nicely, even if the air is cold, the outside air is cold. So there's a lot of strategies. Once I identified this exponential bioplastic greenhouse concept, it was like, okay, now how do you heat these greenhouses? So I just went down the next constraints and got lucky in a lot of places that I had no knowledge of GCRs and plastic mitigation and stuff like that. Yeah, I've been chipping away at that. And that's where I stumbled across this potential of doing really long range lunar logistic operations.
Very cool. I'm glad you went down that path because this has been fantastic. We do have another question from Scott Johnson. What is a better insulator, regolith or space?
Well, a vacuum, you're not going to have any convective loss, right? So if you have a mirrored environment with a vacuum, that would be a pretty good insulator. But no, space, you lose all that heat. You don't have any input of heat. It's just radiant loss. So raw insulation, yeah, the regolith would be more insulating if you were surrounding yourself with that versus the darkness of space.
All right. I believe that is all the questions that we have in our Q&A. So at this point, I believe we can show some closing slides with info on how to get involved in the IPN SIG. So please check out our other keynotes and events. So we are a chapter of the Internet Society, but also operate as our own 501c3, I believe. So please contribute so that we can continue all of these very cool projects and bring all of our members from across the world into a shared space conversation. We have over 1,000 members, but we can also have over 1,000 members plus you. This will take you to a survey once we are done. Thank you all for attending, and thank you so much, Daniel. This has been fantastic.
Thank you.